This is video number 92 in our series on tensor calculus. In previous videos, we've analyzed surfaces and curves that are embedded in three-dimensional Euclidean space. In this video, we're going to move on and perform the analysis for curves that are embedded in surfaces. We'll start with a curve embedded in a simple plane. What we have is a one-dimensional submanifold embedded in a two-dimensional ambient space. Now we can approach this configuration in either of two ways. First of all, since this is a curve embedded in a Euclidean ambient space, we can simply apply all the relationships we derived for a curve using the plane as the ambient space. All we need to do is to replace the z-coordinates, such as zi, with s-coordinates, such as s alpha, and the corresponding shift tensors, such as zi phi, would become s alpha phi. So making all these substitutions into our curve equations would yield the results that we're looking for. An alternate approach is to treat the curve as a hypersurface. This works because the codimension between the plane and the curve is 1. The plane has 2 dimensions, the curve has 1 dimension, the difference between them is simply 1. The ambient space is the plane and the hypersurface is the curve. What we do here is to apply all the relationships for embedded surfaces and replace s-coordinates such as s alpha with u-coordinates such as u phi. We'd also replace the ambient coordinate zi with our surface coordinates s alpha, and shift tensors such as zi alpha would become s alpha phi. Now in this case, the tangent plane becomes a line that is tangent to the curve like this, and the normal is orthogonal to it like this. Now note that we're using the lowercase n for the normal to distinguish it from the surface normal. Either of these methods is a trivial matter of substitution into results that we've already derived, and each will yield exactly the same results. For example, the normal here for the surface analysis is identical to the principal normal used for curve analysis. Okay, well let's see how all this plays out. Regardless of which method we choose, we start by establishing a position vector with an origin located at some arbitrary point somewhere within our ambient space. Now you'll remember that our covariant basis vector for the curve, that's u phi here, is equal simply to the partial derivative of this position vector with respect to our coordinate value. So the partial of r with respect to u phi. And that'll give us a basis vector that is tangent to our curve right here. Well, this can also be expanded using the chain rule and our surface coordinates. So this would be equal to the partial of s alpha with respect to u phi times the partial of r with respect to s alpha. And of course, this first factor is nothing but our shift tensor, s alpha phi, and the second factor is our covariant basis vector for our surface coordinates, s alpha. All right, well, now let's take the dot product of both sides of this equation with itself. And of course, I need a different letter for the second factor here. So we'll have u phi, our basis vector, dotted with u psi this time. And on the right-hand side, the first factor is just this, s alpha phi times s alpha. We're going to dot that with an expression for our second term. So I need a different letter. We'll use beta here. So here we'll have s beta psi times our covariant basis vector s beta. All right, well, the left-hand side is nothing but our definition for the covariant metric tensor for the curve. This is u phi psi. And on the right-hand side, Dotting these two basis vectors, S alpha and S beta, gives us the covariant metric tensor for the surface, S alpha beta, and then we have the two shift tensor factors to include here, S alpha phi and S beta psi. So what we have now is the covariant metric tensor for the curve expressed as a function of the covariant metric tensor for the surface times these shift tensors. Now, all this is exactly how we went about analyzing embedded surfaces. We used this result to define the contravariant metric tensor, then the volume element, and so forth all the way down the line. So there's nothing new about a curve embedded in a plane. It's all stuff we've done before. The question we want to ask now is this. Does this approach work if the ambient space is a curved surface instead of a simple plane? Well, the answer is no. And that's because we cannot define a position vector on a curved surface. So for that configuration, we're going to have to use a different approach. We'll start by recalling a couple of expressions we derived earlier. This is one that we derived back in video number 62. It tells us the surface covariant metric tensor is a function of the z-coordinates. Well, we derived something similar in video number 88 regarding the curve. This is the covariant metric tensor for the curve, again expressed as a function of the z-coordinates. Now you'll recall that we can express our coordinates z as a function of our curve coordinate u, and we can also express it as a function of our surface coordinates s. And there is a relationship, of course, between s and u, so s can be expressed as a function of u. So this relationship allows us to find the partial derivative using the chain rule. This first term is our shift tensor z I phi. This term is shift tensor z I alpha. And this last term is our shift tensor s alpha phi. So what we've got here is a relationship between three different shift tensors. One that relates our z-coordinates to the curve, another that relates our z-coordinates to the surface, and the third one which relates our surface coordinates to the curve. And they're related according to this chain rule. Now, before we go on, let me say that because this is a tensor relationship, we can invert all of these indexes and find a similar relationship using the inverse of each of these shift tensors. In other words, z phi I will be equal to z alpha I times s phi alpha. And these are relationships that we'll make use of many times going forward. Now, what we're going to do is to use this expression right here and substitute back into this equation. And we'll use the same form to substitute here. So what we're going to wind up with is this. Our covariant metric tensor for the curve, u phi psi, is going to be equal to zij times this expression in place of this one. So we'll have z I alpha s alpha phi, and then in place of this one we'll have z j beta times s beta psi. Now observe that this factor times this factor and this factor together are the same as this product right there. So we can replace these three terms collectively with this one expression. So it's going to look like this. U phi psi is equal to S alpha beta. That's replacing these three factors with this. And then we have the two shift tensors left over, S alpha phi and S beta psi, like that. And of course you see immediately that this result is identical to the one we got right over here. Now, the difference in this technique, of course, is that we derive this expression directly from this known result and this known result combined with this result. So here we derive the result with only these equations, and we did not rely in any way upon the position vector. And what that means is that we don't have to depend on the fact that our ambient space is flat. In other words, all of these relationships are true whether our surface is curved or flat. It's a general result that's true not only for a plane, but it's also true for any surface whatsoever. Now, that in turn means that all of the results that follow from this expression, such as the contravariant metric tensor, volume element, and so on, are identical all the way through. So the relationships that we've derived for an embedded surface will apply to the relationship between a curve and a surface. A curve embedded in a surface will have all the characteristics that we've already analyzed, even though the surface itself is curved. All we have to do is to rely upon this as our new definition for the covariant metric tensor and bypass any dependency that we have on the position vector itself. Now, this technique works all the way through using these expressions. So let's see how it works in relationship to our Christoffel symbol. We'll start with this expression from video 90. It tells us how to compute the Christoffel symbol for the curve from that of the ambient space using all of these appropriate shift tensor factors. Okay, well, let's pick on this term right here. In this term, we can replace this and this with the corresponding values using the chain relationship that we derived just a few minutes ago. For example, z phi I can be written as z alpha I times s phi alpha. So this product is the same as this. And then we'll have the partial derivative with respect to u theta, and this term can be represented as zi beta times s beta psi. Okay, so having done that, we'll then expand this out using the product rule. Okay, next we're going to expand this factor out using the chain rule. So this one factor can be represented as the partial of zi beta with respect to s omega times the partial of s omega with respect to u theta. And of course this second factor is nothing but a shift tensor, so that's equal to the partial of zi beta with respect to s omega times the shift tensor s omega theta. So we're going to replace this with this expression right down here. And in the process, I will reorder the terms a bit. So this first term is z alpha I. We'll put this term next. Partial of z I beta with respect to s omega. And then we'll tag on all the remaining shift tensors. So first is s phi alpha. Then we'll put s beta psi. And finally, this new shift tensor factor here, s omega theta. Okay, so don't let me lose you here. All we're doing is this factor and this factor combined are the same as this one. So that's all we've done right here. Now in the second term, you'll notice a contraction here and here. And when we contract these two shift tensors, what do we get? We're going to get a delta alpha beta. And this delta factor will absorb this index to change it to an alpha. So this second expression reduces simply to this. It's going to be this remaining shift tensor s phi alpha, and these two combined to absorb this dummy index is just going to leave the partial of s alpha psi with respect to u theta. Okay, so what we can do now is to replace this term right up here with the sum of these two terms right there. So again, we're replacing this term with this, which is what we derived right down here. Next, we'll make reference to this expression, which we derived in video number 69. This tells us how to derive the Christoffel symbols for the surface if we have those in the ambient space, along with all of these corresponding shift tensor factors. All right, well, now look what happens when we multiply this term by these three factors right here. When we do this, we can make use of our chain relationship for shift tensors to reduce the expression. For example, this factor combined with this one will give us z phi I. This one combined with this one will give us z j psi. And this one combined with this one will give us z k theta. So this entire expression would reduce to this form. So these factors multiplied by this term will give us this term. Therefore, given this expression right here, we can say that this term would be equal to this one times these factors minus this term times the same three factors. At this point, we see that this term is identical to this one, so we can replace it with these two terms, and in the process, it's obvious that this one will cancel this one. So this is going to be equal to simply this term plus this one. All right, what do we have here? Well, we started with these two known relationships, and we derived this one, using nothing more than the chain relationships for our shift tensors. Now, notice that this result is exactly what we'd expect for a plane surface. For that, we'd simply start with this relationship up here, and we'd replace all the z's with s's and change indexes I, j, and k to alpha, beta, and omega. Now, since our derivation did not reference the position vector in any way, we can conclude that the result is true for all surfaces in general, whether they be flat or curved. Okay, well, with that, let's wind the video down with one final derivation. What we'll do is take the partial derivative of this expression, which we derived earlier in the video. And of course, on the right-hand side, we're going to have to make use of the product rule. In this first term, we'd like to express this factor as a derivative with respect to surface coordinates, so we'll employ the chain rule here. Remember that this factor is actually the partial of s omega with respect to u theta. So this factor, taken together with this one, is nothing but the chain rule, the combination of which is the same as this right here. So that's how we can make this substitution. In this second term, remember that S alpha sigma is really the partial of S alpha with respect to U sigma. So when we take this additional partial derivative, we're actually forming a second partial derivative. So what we're saying is that this factor is identical to this factor right here. And of course, we can make the same substitution for this factor right over here. Now we're going to permute the indexes. We're going to rename sigma to theta, psi to sigma, and theta to psi. We're also going to permute the surface indexes. So we'll rename alpha to omega, beta to alpha, and omega to beta. Okay, we're going to do the same thing one more time. We'll permute both the curve indexes and the surface indexes. Next, we're going to add this equation, and we're going to subtract this equation. Now, on the right-hand side, let's first of all consider these three terms. Notice that they all have the same set of shift tensor factors. They're in a different order, but the factors are common to all three of these terms. So here we can collectively add this, subtract this, and multiply the quantity by this set of common factors. But if you remember back, the Christoffel symbol of the first kind for a surface would be equal to 1/2 of this term plus this term minus this term. So collectively, these three terms together can be written this way. It's going to be twice the Christoffel symbol for the surface of alpha, beta, omega times our set of common factors here. So S alpha, sigma, S beta, psi, and S omega, theta. Okay, so this term right here is the same as the sum of all these three. And that's because this Christoffel symbol of the first kind is equal to 1/2 of this factor, minus this factor. Now compare this term to this one. If we rename alpha to omega here, then you can see that these two terms are equal. Because remember, we can switch the order of these indexes, and the order of differentiation doesn't matter. So these two terms are equal. And since we're subtracting this line right here, that means that these two terms, this one and this one, cancel each other out. Okay, well, the same thing happens right here and here. If we rename here alpha to beta, this becomes a beta up here. And you can see that we can swap these and we can swap these two, and they're equal. And again, we're adding this one, subtracting that one, so the two of them cancel out. So this one cancels out with this one. Okay, and finally, this guy right here is equal to that one. If we rename beta to omega here, then again we play the game of swapping the indexes here and the order of differentiation, so these are equal. However, we're adding these two together so they don't cancel each other out, but what we have is twice of these. So that's going to resolve to this. These two added together are going to give us 2 times either one of them. We'll just use S alpha beta times S alpha sigma times the second partial of S beta with respect to U psi and U theta, like this. Okay, so all 6 of these terms resolve down to this one term right here. Now multiply through by 1/2 of our contravariant metric tensor. So I've simply multiplied through by this factor, and of course we see it here and here, the 1/2s cancel the factors of 2 up here. Okay, so look at the effect here. First of all, alpha is a dummy index, And as always, we can raise one of the dummy indexes if we lower the other one. So we'll swap positions for alpha here. And our contravariant metric tensor here has the effect of raising sigma up into the position with phi, like this. Okay, and over here, our covariant metric tensor will lower the alpha index down here to give us beta, and the contravariant metric tensor here will raise sigma, giving us phi right here. So we'll perform all of these actions, and I'll also reorder the expression a little bit. I'll put this term on the left. This term will equal this term minus this one. I've also changed this form to this form. You'll remember that these are equivalent. They mean exactly the same thing. Now refer back to this expression which we derived earlier in the video. Since this is equal to this, we can replace this term with all of this. And in the process, this term will cancel this one. These are equal and opposite because we can rename beta to alpha here, and they'll cancel each other out. The result is the only thing left on the right-hand side is this one term right here. All right, well, all of that was pretty tedious, and you may have to go back over it a couple of times to make sure you follow all the steps. However, they were all very straightforward, and what it amounts to is this, that if we're given this expression, if we know this is true, then what we did here was to derive this expression as a result of it. Now, it would also be true that if we knew this were true, we could derive this expression. In other words, these two expressions are equivalent to each other. They mean essentially the same thing. And of course, this form right here is exactly what we'd expect if we had a curve embedded on a plane. So this tells us, since we didn't use any reference to the position vector, that this expression here is generally true whether the surface is curved or flat. All right, so let's break here and go review what we've done in this video. The first thing we did was to derive some simple relationships using our shift tensors. This is a shift tensor that relates the curve to the ambient space. This relates the surface to the ambient space. This relates the curve to the surface. And what we're saying is this contraction is equal to this one. It's sort of a chain rule relationship. This shift tensor is equal to this chain relationship. Now the same is true for our inverse shift tensors down here. It works in both cases. We then went on to derive several relationships relative to curves embedded in surfaces. Now the critical point of the video is that these results are derived strictly from these chain relationships in conjunction with results we already knew about how curves and surfaces are embedded in three-dimensional space. We did not reference a position vector in any way. That means that these results are generally true for all surfaces, not just planes. Now, since we already understand that these relationships are true for plane surfaces, it follows that everything else that derives from them is also generally true. That includes the contravariant metric tensor, volume element, covariant derivative, divergence, Riemann tensor, and so forth. We can simply apply what we already understand about curves embedded on planes to surfaces in general. We don't have to deal with any special considerations for curved surfaces. Well, let me end with one final point. Note that there's no reference here to z-coordinates or any of its corresponding objects. All the analysis for curves embedded in surfaces derives from the surface covariant metric tensor and the parametric relationship between the s and the u coordinates. There is no reference to extrinsic curvature information. In other words, we don't need to know the details of how the surface is embedded in the ambient space. We only need its metric tensor, and that is an intrinsic object.